Vibration analysis. Procedures for accurate evaluation of machinery condition. Special tests. Synchronous time averaging or STA. Since frequencies add, subtract, mix, and beat, and various combinations of some frequencies equal other frequencies and/or harmonics of other frequencies, accurate analysis is difficult, errors are made, and some problems are overlooked. In these situations, synchronous time averaging must be used to identify and isolate the contribution of each vibratory component. Synchronous time averaging is required for accurate diagnostics of: Number 1, press and calendar rolls in paper machines. Number 2, embossing/pattern and backup rolls in converting and plastics plants. Number 3, work and backup rolls in rolling mills. Number 4, certain gear problems. And number 5, defect size in anti-friction bearings. The equipment required includes various transducers, a high phase or a once per revolution trigger, and a real-time analyzer capable of synchronous time averaging or STA by triggering from an external trigger or the time domain signal. Arithmetic averaging, as accomplished by most analyzers, randomly fills the memory with data, performs a fast Fourier transform or FFT, and stores the data. As soon as these functions are completed, the analyzer starts filling the memory again, performs the other functions, and presents an arithmetic average of all samples taken. This is required in all applications to provide signal enhancement because all frequencies may not be present in every average of the data. The amplitude of each frequency can vary from average to average. Synchronous time averaging synchronizes the start time for filling the memory, with an external trigger or a repeatable distinctive event in the time signal. The memory is filled, and the data is stored. The next average is not started until the next trigger arrives. The memory is filled again, and the second average is combined with the first average. This process continues until the total number of required averages is completed. Since each average is started at trigger time, and the trigger or event occurs at shaft speed or during another event such as ball pass frequency of the outer race, etc., then all vibration related to the trigger/event should be in phase for every average. When the new data is compared with the stored data, all frequencies in phase with the trigger are retained and all frequencies out of phase with the trigger are subtracted out of the data. This means all frequencies occurring at event, trigger, speed or some exact multiple of event speed are retained. It also means that all frequencies that are not an exact multiple of event speed are averaged out of the data. Figure 51 contains the frequency spectrum and time signal of three frequencies: felt speed equal to 0.47 Hz, roll 1 speed equal to 6.7 Hz, and roll 2 speed equal to 7 Hz. The time signal displays the frequencies before they are mixed. Point 1 is the 0.47 Hz signal, point 2 is the 6.7 Hz signal, and point 3 is the 7 Hz signal. At the beginning of the time period, the 6.7 and 7 Hz signals are in phase. However, at the end of the time period these two signals are out of phase. Since the time period between the 0.47 Hz signal and the other two signals is large, the lower frequency is always out of phase on either half of the cycle. Figure 52 contains the same signals after 4 averages. This averaging was performed by triggering off the roll rotating at 6.7 Hz. Note that the amplitudes of the 0.47 and 7.0 Hz signals are reduced by 50%. Figure 53 contains the same signals after 100 averages. The 0.47 and 7.0 Hz signals are still present, however, the amplitudes are now reduced by 90%. Since most frequencies will be in phase for some period of time during the averaging, it is hard to remove 100% of the non-synchronous signals. If we define the synchronous data as the signal and the non-synchronous data as noise, then the signal-to-noise ratio is improved by the square root of the number of averages, where usually abbreviated as n. Some examples of synchronous vibration are: Number 1, speed of the roll used as a trigger. Number 2, gear mesh frequency. Number 3, blade or vane pass frequency. Number 4, sideband frequencies caused by eccentricity. And number 5, frequencies generated by bars on rolls. Some examples of non-synchronous vibration are: Number 1, speeds of all rolls and shafts not used as a trigger. Number 2, noise. Number 3, bearing frequencies. Number 4, some sideband frequencies caused by looseness. And number 5, some harmonic frequencies caused by looseness. If a real-time analyzer will trigger from the time signal and the time signal contains a repeatable distinctive event, such as a defect on a bearing inner race or outer race, synchronous time averaging can be performed. For example, if a bearing has a defect on the outer race, synchronous time averaging or STA sources using the time signal for a trigger could remove most of the vibration not related to the bearing defect. The sources of the data removed could be shaft speed and harmonics, gear mesh frequency, blade/vane pass frequency, and other bearing defect frequencies. The resulting improved signal facilitates a more accurate diagnosis and description of the problem. For more examples of synchronous time average data, please refer to the last chapter of these vibration analysis video that would talk about analyzing and solving press roll and nip problems. Thank you.